title is called momentum. And maybe that's a word you've heard before. To be a little more accurate, it is called linear momentum, or even translational momentum. And it is simply a product of two quantities we've already been working with. And so I'm going to start the chapter and introduce you to a new quantity. It's a very useful and important quantity, as you will soon see. It is really easy to define because it is just made up of two quantities you already know of. In fact, you've already had a discussion and a symbol for mass, and we've already had a discussion and a symbol for velocity, so I'll just put the m and the v here. The product of those two is called the momentum, the linear momentum, and the traditional symbol is p after the Latin. That one's not so obvious. But that's going to be our definition. And if I just start off then and saying, all right, here's a new quantity, of course you're probably asking what's the usefulness of that, and so I hope before the chapter's over I'll get that across to you, what's the usefulness of it. But just to kind of go through those four steps and say, okay, what is the new quantity? What is the formula? What are the units and what do they mean? Let me just do a quick and silly, maybe, calculation. Well, let's just say that I took an object, and so I'll take this cart here, and I put it here on this track, and I push it along, and it moves along, and that was kind of a slow speed. If you remember, these carts are 1/2 kilogram, and I didn't give it much of a speed, let me just say 2 meters per second. So if I came over here and said, okay, what was the momentum before it, crashed in over there, I would say, okay, the mass is 1/2 kilogram. Its speed, or I should say velocity, is 2 meters per second. And if I multiply those together, and I pick some easy numbers, so I can do it in my head, 0.5 times 2 is 1. 1 what? Well, there's really nothing that can be reduced or canceled off or simplified. Oops, no square. And so it is just a kilogram times a meter per second. And surprisingly, that's it. We don't name it anything like we did for the Newton. And in fact, as we go along, you'll see a lot of our new quantities we start naming after the great scientists. You just seen that for the first time with Newton, but you're about to see a joule, you're about to see a watt. You're probably familiar maybe a little bit with volts, maybe amps. Maybe you're familiar, I don't know if you're familiar with Henrys, but all these units as we continue on here are named a lot of times after the great scientists in the field. But at the beginning part, where they go back before Newton and momentum goes back before Newton, we don't give it a special name here. So that's it. And so, like I said, the idea of momentum is pretty simple. And it is also extremely powerful. So that's what I want to illustrate here. But that would be my simple calculation. Now, I do want to point out, notice that I said velocity, not speed. And so let me take you back to chapter 2. What is the difference between velocity and speed? And velocity has direction with it. So that means momentum is also a vector. That means momentum also has a direction. And you'll see that here in a couple of the little experiments I do here. But this really would be saying that that cart had a momentum. This is how I would say it. That cart had a momentum. As it was moving along, it had a momentum of 1 kilogram meter per second to the right. It was moving to the right. And so maybe I'll just say to the right. And so again, just want to emphasize, it is a vector. It has a direction. It's also a number, but it also has a direction. And as we had said, direction can be just as important as the numbers. And so more on that in a minute, but why do we care about it? Watch this. The net force is equal to mass times acceleration. And acceleration then is the change in velocity divided by time taken. And change in velocity is often written as final velocity minus initial velocity over time taken. And if we do the distributive property with our math, we would have mass times the final velocity minus mass times the initial velocity. And maybe now you're beginning to see this quantity of momentum come into play, right? There it is. There's a mass times a velocity. There's the two of them together. That's why we are defining this new quantity of momentum as the product of the two. I'll keep going. Because I could then simplify this and call this the final momentum and this the initial momentum. And maybe to make this equation look a little bit nicer, I will move this to the other side. And so this would be the net force multiplied by time is then equal to the change in the momentum. And so I would say that this really is just another way of writing Newton's second law, but a very useful, very powerful way. And so I want to keep emphasizing, that's why this is kind of a short chapter. The only thing I'm going to do here in this chapter is define this new quantity called momentum. And I'm going to be looking at a lot of the things we've already looked at, but through another lens. A lens that doesn't look at velocity, but a lens that looks at momentum. And so if you let me get started here before we take our break here, this is saying what? Well, it's saying to change the momentum of something, you need a force and a time. You need both of those. And so if I come over here and I say, all right, can I change the momentum of this cart? You see, right now, if I took this cart, I would say this cart has zero momentum. Because remember, momentum is mass times velocity. And right now the velocity is zero. Okay. To change it, to make it a positive number, I have to give it a force. And that's where my hand would come in. And so as I push on it, my hand, for a short amount of time, my hand changes its momentum. And so I would say that I am putting a force on the cart for a period of time. And what that did is changed its momentum. It increased its momentum. Now, before this chapter, you would have said, oh, well, your force on the hand would have given it an acceleration. Yes, exactly. And I don't want you to forget that. That's useful, very, very useful, because in that case, you're looking at motion, and that is useful. That's Newton's second law. But this is also very useful. I need to go to our break here in just a second, so I'll continue this conversation after our break here. But I would say that I am giving it some momentum. But think about what happens now when my hand stops pushing on it. And so I come back over here and my hand is no longer pushing on it. And so here's the first part. Now my hand, right there, see, there's no force on it. And this would say if there's no force on it, there's no change in momentum. And so this thing would just keep going with the same momentum. And momentum, of course, is mass times velocity. And of course, you would have said before this chapter, you would have said, well, isn't that just Newton's first law? Yes, it is. Isn't Newton's first law just saying if you don't put a force on it, an object will keep its same velocity? Yes. And so I don't want you to forget that. That's a way of looking at it. Very useful. You're looking at motion. You're not looking at momentum. But I would say then without a force, I would not change its momentum. So that's why it keeps going at the same velocity. And it just keeps going that way until there's another force on it. And in this case, it collides into this bumper at the end, and that bumper puts a force on it. And then, of course, that changes the momentum. And in this case, it reduces the momentum. And so increase momentum, constant momentum, lose momentum. And so what I want you to get out of this is you will only gain or lose momentum when there's a force. If there's no force, you keep whatever momentum you had. Now, I'll finish with kind of this point that a lot of times you may be interested not so much in the momentum change, but in the force. So if I rearrange this equation and say force is then equal to the change in momentum over the time taken, what might happen if this? Let's say I go to a baseball game and somebody hits a foul ball and it's coming right at me. And I've always wanted to get a foul ball. I've never gotten one, but I keep hoping someday one will come right to me. Oh, by the way, last summer, so close. I was, had my whole family. My son was about 4 seats over. It was a home run ball. And I'm like, hey, 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 hey. And my son wasn't even paying attention. And he was looking this way, talking with his buddy, and the ball went right between their two faces. Just, I was like, oh! I'm glad you weren't hit. That's what's lucky. And then the guy behind us got the ball. But this is our chance to get a ball. Well, anyways, I digress. But look at this baseball. If I wanted to catch this baseball, one of the things I'm going to be concerned with is it going to hurt? Am I going to break my hand? I mean, I want a baseball, but I'll give up the baseball if it's going to give me a broken hand. I really don't want the broken hand. Is it possible for me to catch the baseball without breaking my hand? Is it possible for me to get in an accident in my car at, say, 45 miles an hour and not get injured? And I want you to see something quite interesting here, because this right here is what I'm getting at, this factor of time. We call this the stopping time or the contact time, because when you go to stop this baseball, the change in momentum is kind of set, right? The baseball is coming, and the mass of the baseball and the speed of the baseball as it comes in is set. And if you're going to catch it, you're going to stop it. So you're going to go from some value of momentum to zero. The change in momentum is determined by those initial conditions. Now, I can hope that the baseball is not coming very fast, and therefore the change in momentum is small. And you can see that if the change in momentum is small, then the force needed to stop it is small. That's good. Or if the mass of the baseball is small, which instead of maybe a baseball, maybe somebody hit a tennis ball at me. That would, be a little bit better. That would be less mass. Or better still, a ping pong ball. And so all of those would result in a smaller number. But as I sit in the grandstands and I'm waiting for this baseball to come my way, so finally my chance, here comes that home run ball. The speed of the ball and the mass of the ball is already determined. If I want to stop it, I want the final momentum to be zero. So that number is set. Is there anything I can do to reduce the force? And the answer is yes. Look carefully. Isn't it the time it takes to stop it? And so if you've ever played that game at a picnic where you'll take an egg and play catch with it, or a water balloon and play catch with it, the key to keep the water balloon or the egg from breaking is you reach out and you grab it, and as you stop it, you kind of what we call move with it. You put out your hand and you roll with it. You take that egg and you make a lot of contact time. Because interesting enough, the amount of force on your hand is not completely determined by the speed and the mass of the object coming towards you. It's also determined by how much time it takes to stop it. And so if somebody tosses an egg to me, and I don't really know how to play the game really well, I might just go, oh, got it. And if that egg hits and you grab it, that short amount of contact time is a huge force, and that egg breaks. And you lose the game, and the other people who haven't broken it go on and play the game. And so if you really want to get that egg, you have your friend toss it to you, and you go, whoa, got it. And you give it a lot of contact time. And that's the idea of an airbag. You go on 45 miles an hour, and now you want to stop. And if you don't have an airbag, if you have an old car without an airbag, what ends up happening is you move forward and you hit the steering wheel, and you stop in a short amount of time. And that's going to take an enormous force. And that enormous force on your body does a lot of damage. But on the other hand, if the airbag is inflated, then you will come to a stop over a much longer period of time. And so the amount of force can actually be radically different. And so it's surprising that a head-end collision with no airbag, one person could die, and the other one's, barely shaken up, no injuries, no blood, just maybe a little psychologically shocked by, whoa, what just happened? I just crashed my car into a wall. And so the amount of force can very, very, very much change. You really see that really well in race cars. Race cars, even modern cars, they have crumple zones. And the whole idea is when that car hits, parts will break off and squish together. And some of these accidents can look horrendous. Volvo does a great job of it because they've got these special mounts for the engine. If you do a head-in collision on a Volvo, the engine itself actually disengages and falls. And the whole engine just goes crunch, crunch, engine compartment. Crunch, 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 crunch. And the amount of contact time is huge. And the amount of force then is small. And so you just did this head-in collision, 70 miles an hour into a wall, and you open the door and walk out going, wow. And of course the accident looks terrible because the whole engine has fallen out of the car, it's down on the ground, the whole engine compartment is then squished up to this little tiny thing, looks like an accordion if you know what those old instruments are, and you just open the door and walk out. And so, well, I've talked a lot here, so we need to take our break. So let's take our 20-minute break, and when we come back, we will keep talking about momentum, and we will get to the main part of this chapter, why the momentum, and particularly the change in momentum, is such a useful and powerful tool. All right, so see you in 20.